Good day, students. Today we shall look into the Raman spectrum for pure rotational motion of linear molecules. We have seen that the molecules, when they are excited by using electromagnetic waves in the visible light region, they may be excited to higher energy levels, and they may simultaneously have rotational or vibrational motions together. Now let's look into the pure rotational motion of linear molecules and the Raman spectrum obtained from it. Now the rotational energies of a linear molecule was earlier defined as eta j is equal to the rotational constant B into j plus 1 minus the centrifugal distortion constant d into j square into j plus 1 square centimeter inverse, where j is the rotational quantum number having integral values from 0, 1, 2, 3, etc. Now for easier discussion, we are neglecting the centrifugal distortion constant d, and the expression will be eta j in terms of wave number is equal to b into j plus 1 centimeter inverse. Now we have defined the energy levels. Now this molecule, when it is excited, it can obey only certain selection rules, and they are given below. In microwave spectroscopy, the selection rule was that the change in the rotational quantum number can be only plus or minus 1. That is, delta J can be only plus or minus 1. But whereas in Raman spectroscopy, the molecules can be excited to J plus 2 levels or J minus 2 levels, or they can remain invariant in their energy levels. That is represented as delta J is equal to 0 and plus minus 2. That is, in Raman spectroscopy, the rotational quantum number changes by 2 units rather than 1. And this is because of the symmetry of the polarizability ellipsoid. We shall look into it. Now, for a linear molecule, it is clear that during the end-over-end rotation, like when this molecule 1, 2, that is bonded by this bond length, if it undergoes end-over-end rotation, means if it is rotating like this, here the ellipsoid has the same appearance to an observer twice in every complete rotation. Let's look at it. Now assume this molecule in this orientation. Okay, so here the polarizability will be maximum in this axis. Hence, the ellipsoid will have the least distance in this axis. Polarizability will be minimum along this axis. Hence, the ellipsoid has the maximum distance in this direction. And thus we get the polarizability ellipsoid. Now when it undergoes rotation by 90 degree, it comes into this shape. Here the ellipsoid shape will be defined as, in this direction, polarizability being maximum, here the ellipsoid will have minimum distance. Whereas in this direction, the polarizability being minimum will have the maximum distance in the ellipsoid. Hence, polarizability ellipsoid takes this form. Now again, when the molecule is rotated by 90 degrees, here the polarizability is maximum in this orientation. Hence, the ellipsoid has minimum distance in this orientation. And when the polarizability is minimum in this orientation, the ellipsoid has maximum distance in this orientation. So here we can see that in the first case and in the third case, the ellipsoid is taking this shape. It is coming twice in this shape, but it is appearing the same to the observer. Now in the fourth case again, when the molecule rotates another 90 degree, it comes to this position. The polarizability being maximum in this orientation is represented with the least distance in the ellipsoid here, and the polarizability having the minimum in this orientation is represented by the maximum distance in this orientation. Likewise, the second case and the fourth case shows us that the ellipsoid has the same shape, and the observer will be seeing the same shape twice in one complete rotation. This is why the selection rule delta J is equal to +2 is taken into consideration. Now, the rotation about the bond axis produces no change in polarizability. It means that if this molecule is rotating along the bond axis itself, the one molecule is just rotating over it and the two molecule is just rotating over it. That is, the rotation is along this axis. There is no change in the polarizability, and hence it does not give any Raman spectrum. Thus, only end over end rotations, only they give Raman spectrum. Now, for a pure rotational change, the transition delta J is equal to -2, it is ignored. This is because the upper state quantum number must necessarily be greater than the lower state. Okay, that is, if we have the condition J is equal to 0, delta J is equal to -2 is impractical, right? We do not have any J equal -2 levels. So it is impractical. Moreover, we are having the molecule to be excited to the upper states. So delta J must be equal to +2, cannot be equal to -2. And delta G equal to 0, that represents no change in the molecular energy. That means that the radiation is falling on the molecule and it is just being scattered. And there we obtain the Rayleigh scattering. So for delta J equals 0, we get Rayleigh scattering. Now let us consider the transition of delta J equals +2. Here the change in the energy delta eta is given as eta for J prime equals J plus 2 minus eta for J double prime is equal to J. Now putting the values of J in this equation. Okay, so we have the expression for eta J is equal to B into J plus 1, right? So here I am taking the difference of the upper level minus lower level. So I get the value of eta for the upper level as B into J plus 1, that is J plus 2 into J plus 2 plus 1, that is J plus 3. This is the energy of the upper level minus B into J plus 1. Now taking the products, this is written as B into J square plus 3J plus 2J plus 6 minus Bj square minus B. Rearranging, we get Bj square plus 5Bj plus 6B minus Bj square minus Bj. Here we have this term 5Bj minus Bj, that gives 4Bj. Bj square and minus Bj square cancels out and the remaining term plus 6B. Hence, taking B outside, I get B into 4J plus 6 centimeter inverse. Now, here we have taken delta J is equal to +2. So, these spectral lines is labeled as the S branch lines, and thus we write delta eta of S branch is equal to B into 4j plus 6 centimeter inverse, where j is the rotational quantum number having integral values 0, 1, 2, 3, etc. Here j represents the rotational quantum number of the lower state. So here let us understand that if this molecule, it gains rotational energy by the light incident on it, we have a series of S branch lines to the lower wave number side of the exciting line. Okay. Now, if the molecule loses energy to the incident light, we have the S branch lines on the higher wave number side of this exciting line. That is our Rayleigh line. Okay. So the lines on the lower wave number side, that is on the lower frequency side, that is the Stokes lines. Whereas the lines on the higher wave number side, that is the higher frequency side, that is called the anti-Stokes lines. So let us generalize this expression for the wave numbers of this S lines as nu bar of S is equal to nu bar of the exciting radiation plus or minus delta eta of S lines. That is nu bar of the exciting radiation plus or minus B into 4G plus 6 centimeter inverse. Here the plus sign refers to the anti-Stokes lines, higher frequency side lines, and minus sign refers to the Stokes lines, the lower frequency lines. And the nu bar of the excitation radiation is the wave number of the exciting radiation. Okay. So if our nu bar S is equal to nu bar exciting radiation, this represents the Rayleigh line. And for the other lines, first let us give the value j is equal to 0 in this equation. So what we get is nu bar of S is equal to nu bar of the exciting radiation plus or minus, this term becomes 0. We get 6b. So here we can see that the separation of the first line from this excitation line, from this excitation Rayleigh line, the distance of this first line is 6b. For plus 6b, it is on this position, anti-Stokes line, first anti-Stokes line. For minus 6b, it is this line, the first Stokes line. Okay. Now let us give the value j equals 1. So for that we get nu bar of S is equal to nu bar of this exciting radiation plus or minus B into 4 plus 6, that is 10B. So we get the next line at the 10B position, plus 10B position here and minus 10B position here. For j equals 2, we get nu bar of S is equal to nu bar of the exciting radiation plus or minus B into 4 into 2, 8 plus 6, that is 14B. So here the third line is placed at 14B on the right side and Stokes lines is placed at 14B on the left side. Now let us calculate the distance between these anti-Stokes lines or the Stokes lines. Here this first line is at 6B, the second line is at 10B and the third line is at 14B. Hence the distance between these anti-Stokes lines is 4B. Likewise, on the Stokes-Raman lines, the distance between these lines is again 4B. Here in this spectrum, we have plotted the lines, the spectral lines with frequency or wave number on the x-axis and intensity of the line on the y-axis. That is why we obtain the anti-Stokes lines on the higher wave number side or higher frequency side, and Stokes lines on the lower wave number or lower frequency side. Now, a few points to remember in the pure rotational Raman spectra of linear molecules. For diatomic and light triatomic molecules, the rotational Raman spectrum will normally be resolved. Each spectral line will be apart from each other, and we can immediately obtain a value of B. And if we get the value of the rotational constant B, from that we can calculate the moment of inertia mu, and hence from that the bond length R for the molecules. Now, the next case is that for homonuclear diatomic molecules, that is, for example, homonuclear hydrogen and oxygen diatomic molecules, they do not have the infrared or microwave spectra. This is because they are having no dipole moments, but they will give a rotational Raman spectrum. So in order to study such molecules, we can take a Raman spectrum of these molecules. Now, if the molecule has a center of symmetry, that is, for example, hydrogen, oxygen, carbon dioxide molecules, in these molecules they have a center of symmetry being linear molecules, then the effects of the nuclear spin will be observed in the Raman spectra. Hence, for oxygen and carbon dioxide molecules, since their spin of the oxygen atom is 0, every alternate rotational level will be absent. Hence, in the case of oxygen, the atomic molecule, every level with the even J values is missing. And every transition labeled J equals 0, 2, 4, 6, etc. will be missing from the spectrum. Now, in the case of hydrogen diatomic molecules, since their nucleus has non-zero spins, there the spectral lines show an alternation of intensity. That's all for today's session. Thank you.